Hi, I'm Patrick Rim, and I'm excited to present ProtoDepth, a novel framework for unsupervised continual learning by leveraging learnable prototypes. Depth completion is the multimodal task of reconstructing three-dimensional environments from an egocentric point of view in the form of depth maps. To motivate our work, we can begin by thinking about the real-world applications of depth completion, which facilitates crucial spatial applications such as autonomous driving, augmented and virtual reality, and robotic manipulation. These real-world applications operate in dynamic environments with non-stationary data distributions, but continuously fitting a depth completion model data from novel distributions causes the model to catastrophically forget previously learned information, where the model performance degrades significantly on data from distributions that it had already observed. Robustness and generalizability are crucial for such user-facing systems, motivating continual learning as a needed solution for this problem. Unsupervised depth completion suggests the potential to continuously learn, but to enable pre-trained models to adapt to new environments or domains in an unsupervised manner, we turn to continual learning, where training strategies aim to mitigate catastrophic forgetting while maintaining the ability to adapt to new distributions. In other words, we want to minimize catastrophic forgetting while simultaneously maximizing plasticity to learn from new data, in what we call achieving a stability-plasticity trade-off. Unlike existing continual learning methods, we opt to freeze a backbone model entirely and learn a small set of parameters, which we term prototypes, that modulate the latent features for each new dataset encountered. So now we present ProtoDepth, a novel prototype-based approach for efficient state-of-the-art continual learning of unsupervised depth completion. All current unsupervised depth completion models have this dual encoder-decoder architecture, with one encoder for each input modality and skip connections between corresponding layers of the encoders to the decoder. As terminology, we define the latent space as the bottleneck layer as well as all of the skip connections. To explain how our method works, let's first consider an input sample from a single dataset at a single layer of the latent space, which is encoded into the latent features x of shape h by w by c. We flatten x to get queries q of shape n by c. Since the encoders are entirely frozen, q serves as a set of n deterministic queries, where each query is a c-dimensional vector. We define a projection matrix W that learns to map the prototypes P back into the query space, which is the latent feature space. So the keys K equal the projection matrix W multiplied by the prototypes P. We found that the stop grad facilitates decoupled optimization, enabling prototypes to learn appropriate additive biases, while keys learn to assign relevant prototypes to queries. Using ablation studies, we found that this improves performance. Finally, we compute the similarity scores between the queries Q and the keys K using scaled dot product attention, which are then used to compute a convex combination of the prototypes P, which serve as our local additive bias that we add back to the frozen latent features. To model the global transformation, we learn a c-dimensional multiplicative prototype D applied element-wise, which can be efficiently implemented as a one-by-one depth-wise convolution. So now we can define a prototype set for a given data set as the local and global prototypes P and D, as well as the projection matrix W. Since the model is frozen and a new prototype set is learned for each new dataset, this naturally facilitates continual learning and ensures zero forgetting in the domain incremental setting, where the domain identity is known at test time, since we can apply the prototype set corresponding to the known test time domain. So up here, we denote that the test time domain identity is given in this incremental setting. But how can we extend our method to the more realistic domain agnostic setting, where the test time domain identity is unknown? If domain identity is unknown, then we can't just simply select the corresponding prototype set during inference. To address this challenging scenario, we introduce a prototype set selection mechanism that chooses the most relevant prototype set for a given input. For an input from a certain data set, we can deterministically obtain a sample descriptor by applying global average pooling to the bottleneck latent features with channel dimension C. So for any given input, we obtain a sample descriptor, which is a c-dimensional vector. The key observation here is that, again, since both encoders are perpetually frozen, the bottleneck features are a frozen deterministic function of the input throughout the entire continual learning process. Then for each new dataset, we deploy a new domain descriptor and freeze all existing domain descriptors. Each domain descriptor is also just a c-dimensional vector, so they add negligible overhead in terms of number of parameters. The deployed domain descriptor is trained by maximizing cosine similarity between itself and sample descriptors for the current dataset, while maximizing the cosine distance to all other learned domain descriptors, which we froze. This naturally yields domain descriptors that are discriminative across datasets, allowing us to use the projection of a sample descriptor onto the domain descriptors as a prototype set selection mechanism, where during inference, for a given input, we select and apply the prototype set corresponding to the domain descriptor that maximizes cosine similarity with the sample descriptor. So this is a two-dimensional t-SNE plot of sample descriptors and domain descriptors for our indoor dataset sequence, which consists of the NYUV2, ScanNet, and Void datasets. We see that while most sample descriptors align closely with their respective domain descriptors, some overlap, such as some of the green dots being closer to the red star, enables cross-domain generalization, improving performance in challenging scenarios.